Hello, today we're going to be talking about the conditional and biconditional statement. The conditional. A conditional statement is a statement P implies Q, where P is the hypothesis and Q is the conclusion. As a note, a conditional is false only when the hypothesis is true and the conclusion is false. We will see this in the form of a truth table on the next slide. So we have our P statement, our Q statement, and our P implies Q statement. That's how you read a conditional statement. So we're just going to fill in the truth tables for P of true, true, false, false, and the truth values for Q of true, false, true, false. And then true implies true, that's true. True implies false is false. False implies true is true, and false implies false is true. Again, you'll notice that every value for P implies Q is true, except for when P is true and Q is false. Now, let's do it for a larger example. Like, say, not P or Q, in parentheses, implies not P and not Q. So this is a very large truth table with 7 different statements. We have P, we have Q, we have not P, not Q, not P or not Q, not P and not Q, and the total statement of not P or not Q implies not P and not Q. You'll notice that each value inside the parentheses gets its own column in the truth table. So we start off by filling in the P values again of true, true, false, false. Our Q values of false or true, false, true, false. And the not P values, which is just the opposite of the P values of false, false, true, true. The not Q values, which are the opposite of the Q values of false, true, false, true. Now, as we went over last lesson, not P or not Q is false, true, 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 because we just need one of them to be true for the whole statement to be true. And remember from last lesson, the not P and not Q is only true when both are true. Now, we look at those individual values from the parentheses for the implication. False implies false, as we just learned, is true. True implies false is false. True implies false is also false. And true implies true is true. We can recall that this is not a tautology, just as a fun fact. And now we're going to look at the derived forms. Some of the derived forms are logically equivalent. Well, for example, we can see that the conditional is logically equivalent to the contrapositive. The converse is logically equivalent to the inverse. On the next slide, we will demonstrate this through the use of a truth table. Logically equivalent, by the way, don't forget, means that they have the exact same values on the truth table. So, let's look at the derived form's truth values and how it is written. So the conditional is written as P implies Q. The converse is written as Q implies P. The inverse is written as not P implies not Q. And the contrapositive, as you can probably guess, is written not Q implies not P. So basically we just either flip them or put the little not symbol in front of it. So let's see the truth tables of all of these. P, Q, P implies Q, Q implies P, not P, not Q, not P implies not Q, not Q implies not P. So again, just fill in the truth values for P of true, true, false, false. The truth values for Q of true, false, true, false. The truth values for P implies Q of true implies true is true. True implies false is false. False implies true is true. And false implies false is true. The truth values for Q implies P. That's true implies true is true. False implies true is true. True implies false is false. And false implies false is true. And now we just negate those P values for our not P. And negate the truth values for Q for not Q. And now, to show the inverse, false implies false is true. False implies true is true. True implies false, that's false. True implies true is true. And now let's look at the truth values for our contrapositive. Not Q implies not P. So we have false implies false is true. True implies false is false. False implies true is true. And true implies true is true. You'll notice that the truth values for not Q implies not P are the exact same as P implies Q. And the truth values for not P implies not Q is the exact same for Q implies P. That's why we say the converse and inverse are logically equivalent, and the contrapositive and conditional are logically equivalent. Now let's look at another example, rewriting statements that we have into the derived forms that we just learned. So let's let our statement P be I need food, and Q be I will go to the store. Now, personally, I need food because I'm starving, and hopefully I'll be able to go to the store, but I'm also broke, so we'll see. So the conditional is if I need to go to the store, if I need food, then I will go to the store. The converse is if I go to the store, then I need food. The inverse, if I do not need food, then I will not go to the store. And the contrapositive, if I do not go to the store, then I do not need food. And now let's look at something else, alternative forms. Sometimes you will see conditionals written in the following way. We'll see Q if P, P only if Q, P is sufficient for Q, or Q is necessary for P. So let's rewrite our P implies Q statement of I need food, I will go to the store, in all the different ways that we can that are the exact same, just worded differently. Note, some of these don't make much sense grammatically, but that's okay. So, we start with, if I need food, then I will go to the store. And we go with, next, I will go to the store if I need food. That's the same as I need food only if I go to the store. Or, I need food is sufficient for I will go to the store. That one's one of the really funny sounding ones that doesn't make sense grammatically, but makes sense logically. And finally, I will go to the store is necessary for I need food. Now let's take a quick look at the biconditional. The biconditional gives us that two statements say the same thing. This means the biconditional is true when either both P and Q are true, or both Q and P are false. This is sort of a stronger version of the conditional. And it's symbolized by a double-headed arrow pointing to both P and Q. So let's look at the truth table for the biconditional. Let's start off with our P and Q values of true, true, false, false, true, false, true, false. And end with our P if and only if Q, which is how that double-headed arrow is stated. Of true if and only if true is true. True if and only if false is false. False if and only if true is false. and false if and only if false is true. And let's go back to looking at a more complex example of this. Let's try not P or Q. If and only if, not Q and P. So let's fill in the truth table values for P and Q, and not Q are easy examples. True, true, false, false, true, false, true, false, and the opposite, false, true, false, true. Now, P or Q, we recall, is true or true is true, true or false is true, false or true is true, false or false is false. And let's negate that with not P or Q, and we get false, 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 true. Now let's look at not Q and P. So false and true is false. And again, true and true is true. False and false is false, and true and false is false. Now, combining these two into a biconditional, we see not P or Q, if and only if, not Q and P. False if and only if false is true, false if and only if true is false, false if and only if false is true, and true if and only if false is false. And that's it for the biconditional. Thank you guys for watching.